All right, I think I'm ready. It's time. Welcome back. Thank you for coming. I know it's so nice out. Maybe some people decide to stay outside. It's all right. We're here below ground talking
When
about...
it's this temperature, I really only like being out at like once the sun starts to go down.
Oh, yeah?
Yeah.
I think it's pretty nice out. All right, so I would like to say a little bit more about Euler circuits and Euler paths. That's what we've been talking about lately. Remember, those are paths or circuits through a graph which use every edge but don't repeat any. This is what we were talking about last time. Euler circuits and paths. That is, they use every edge. No repeated edges. And circuit means that it ends up back where it started. Path means that it starts and ends at two different points. All right? This is what an Euler circuit or Euler path means. And if I give you a graph, you can tell by looking whether or not it has an Euler circuit or an Euler path. For example, if I make something like, how about this, with an edge here and an edge like that. Does this one have an Euler circuit, or does it have an Euler path, or does it have neither? Anybody remember how to do that? What are you looking for when you look at the picture? Yeah.
You're looking for like I don't know what it's like. It's not called like an off point, but like there's a certain kind of thing that you're looking for it not to be in an odd quantity.
Yes, that's right. There's a certain quantity which is supposed to be even all the time.
All even degrees will be a circuit, and two odd would be a path.
Yeah, right. It's called the degree. That's how many vertices, how many edges are touching each of the vertices. So for a circuit, all degrees must be even. And for a path, that is an Euler, I'm talking about Euler circuit, Euler path. Two odds and the rest even, right? This is the big takeaway from last time. So this one over here, what I put there, you should just look around the graph and say what are the degrees each time. This, if you know what you're looking for, is easy to tell. That's a 2. Remember, it just means how many edges are touching each of these vertices. This one in the top middle is a 4, because I see 1, 2, 3, 4. You can mark them off if you like. 1, 2, 3, 4 as you go around. There's 4 edges that touch that vertex. All right, the one in the upper corner there is a 2. That's a 2. This is a 4. That's a 2. Once you get used to it, you can do these pretty quick, I think. That's a 4. That's a 4. That's a 4. That's a 2. All right? I hope that I did all of those properly. And so they are all even in this example, which means this one does have an Euler circuit. So here there is an Euler circuit. All right? And I might ask you to draw the Euler circuit. So in this example, I'll just draw the picture again. Usually I draw this by making, a red line going around the picture. It has to start somewhere and end at the same place. And actually, when you're doing an Euler circuit, starting and ending at the same point, it doesn't really matter where you start. So maybe I'll just start up in the top left here. And I hope you remember my little pro tip drawing lessons. Make your line as you're drawing it go sort of next to the lines on the graph. Don't go right up over the graph lines, or else it will be impossible for me to tell what you were thinking. All right? I am just sort of trying to make this up as I go along. Usually you can just make it up as you go, and as long as you don't mess it up, you will be able to make it back where you started. I just used every edge once without repeating any edges. I think I covered all of them. So that is an Euler circuit. All right. Euler path means it's like that. You use every edge, but you start and finish at 2 different points. And the 2 points that you start and finish at will be the 2 odds, right? An Euler path exists when there's 2 odds and the rest are even. And those 2 odds have to be the starting point and the ending point. All right? Any thoughts? This is sort of review from last time. I wanted to do a couple of sort of realistic examples, maybe. I don't know. Vaguely realistic examples. How about, this one is kind of similar looking. Let's say that I have a grid of streets like this. The streets go like that, but then there's a diagonal one right here. All right. Let's say this is a little neighborhood. A street grid, and let's say we have the snowplow guy, Mr. Plow. Mr. Plow wants to plow all of the streets in the best way possible, and let's imagine that he can just go down a street once and it'll be plowed. So my question is, can Mr. Plow drive down each street one time without repeating any streets? Like he doesn't want to go back over the street that he already plowed, right? That's for suckers. So can Mr. Plow drive down each street one time without reusing any streets? That's the question. What do you say?
No.
No. The answer is no. Yeah, I agree. And why do you say no?
Because on the top middle it's 3, so it's odd.
Yeah.
And on the right bottom, both of them are.
Yeah, this is also 3 and also 3.
So
Yeah.
it's-
Yeah, and I think also the one in the middle on the left is also a 3.
Yeah.
Can I just write them all in? These are 2s. This is what you should be looking for immediately when you see a problem like this, is what are the degrees? And it matters which ones and how many are odds versus evens, all right? But this one, we can see it has many odds. So this is impossible. Mr. Plow cannot do it, all right? Whether in a circuit or whether like starting at one place and finishing at another place. I suppose Mr. Plow would prefer a circuit, probably. Especially if Mr. Plow himself lives in this neighborhood. He could just start at his house, end up back at his house. Everything would be great. But that is not possible. And you can't even do it starting one place and ending at a different place. Because there's too many odds, right? That would require only 2 odds. All right. Does that count as a realistic example? I don't know. The real plow guy does not just go once over every street. I don't think. Anyway, here's a little variation. A little, let's say Mr. Plow's lady friend, Ms. Road, she builds roads. And Ms. Road wants to help Mr. Plow realize his dreams. Is it possible to build another road somewhere on the diagram to make Mr. Plow's day? Ms. Road wants to build a new road somewhere. You know, add on to that picture up there. Put in a new road so that Mr. Plow actually, I'll say MP for Mr. Plow, can actually do, what he's always wanted to do, which is driving across one road with no repeats. The question is that possible? And if so, where would you add a single road? What do you think?
In the top left, I'd put a diagonal between the 2 3s.
Yeah, I like that. Yeah, so you should be looking at the odds, right? The odds are what causes the problem in the first place. So maybe considering that the odd ones, maybe I'll circle this guy, this guy, this guy, and this guy. Those are the ones that are kind of bad edges, in my opinion. If it weren't for those ones, then actually you could make a Euler circuit or Euler path. And what she said, this is a good idea, connect these 2 guys up together. If I add a new road right there, this is my new road. What is the effect on these numbers? Well, this 3 used to be a 3, but then I added an extra edge, so now this 3 becomes a 4, right? And I turned an odd into an even, which is good in the opinion of Mr. Plow. So this is now a 4. And how about over there? That 3 also used to be a 3, but now it's a 4 because I added a new edge. Now it's a 4. Is that a question?
Could you also, if you have want to have an Euler path, that you do like a 90-degree on the right bottom?
Yeah.
Down.
Oh, and then also add here
Yeah.
to make an Euler circuit?
Euler path.
Yeah, I think this one already now, once you add that one, it does now have an Euler path.
Oh, then Euler
'Cause
circuit. Yeah.
Yeah, if you want to make it into a circuit, then yeah, you would have to add another edge connecting those two. Yeah. Is that a question?
I think instead of like doing that blue line that you did,
Yeah.
I think if you erased that, like you have it like this, I think if you have it like this, like it would be a lot simpler.
Put the line. I'm not sure I understand. Put the line somewhere else?
I think so. I think you could put one line in between the 3 on the left and the 3 on the bottom.
Yes.
Another one between the one on the top and the one on the right.
Yes. So I mean I said in the question, can we build one single new road? So I think what you just described would work, but I want to only build one road. Although you could have also done it here. I don't know if this is what you were suggesting. Just there, we'll have the same kind of effect. That changes this to a 4 and this to a 4, and then we only have 2 3s left in the top and on the right.
Yes.
So there are several ways that you can make this work. Anyway, let's just pretend the first one was our answer. I mean, this is a good answer also. I just want to say, so sort of the point of this is now it does have an Euler path. All right, because it has only 2 odds, the 2 3s there. Can we draw the Euler path now? Let's see if we can do that. So I'm going to make a fresh one, like so. It's got this guy, and it also has the new one. Now, can you draw the Euler path? Remember, an Euler path exists when there are 2 odds and the rest are even, which is true in this case. The odds are those 2 3s, and if you're trying to draw an Euler path, you have to remember that an Euler path must begin at one of the odds and end at the other odd. So I'm going to start, and it doesn't matter which one you pick, but maybe I'll choose the one on the right. I will start here, try to make my Euler path, and again, you can more or less just make it up as you go along. You actually don't have to try to end at the other one. It will naturally end up at the other one, sort of auto-magically end up at the other one, mathemagically, if you just mind your own business. Make sure not to repeat any edges, and you don't miss any edges. Now you will notice that I already went through this one, which is where I'm going to finish off. That's okay. You are going to have to go through it. I'm going to revisit it. You just can't use the same edges more than once, but you are going to visit the same vertices more than once. Like so. I'm just making that up as I go along. If you made up an Euler path on your own, it would probably look very different from mine. And there are many, many different ways that you could make an Euler path through this graph. But you better start at one of those odds, and it will end at the other one. All right, that's an Euler path. Any other questions about that one? All right, I got one more sort of slightly realistic example. These are vaguely realistic. How about, this is a little bit more abstract, and we'll have to do a little bit more work. Let's imagine this is a city block where I'm actually drawing, like these blocks are like the buildings on a very rectangular grid. And the roads, these are the roads. These are the dotted lines going down the middle of the roads, all right? And let's say we are the mailman, the mail delivery person, and we got to walk around the block to deliver the mail to everybody that we need to get to. Now, Some of the people that we need to deliver to are on either side of the road, and that means some of these roads we're going to have to walk up and down twice because we only walk one side each time. Everybody knows you should only cross at the intersections. You don't cross the street in the middle. So sometimes we have to walk some of these roads twice, and I will show you where the people live. So this is part of the setup. I'm going to put dots. These dots are people that we got to deliver the mail to. So they are here, also here. They're all over this one. They're also here, 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 and here. All right? You can only walk on one side of the road at a time, and you have to get to all the dots. And I ask you, again, is it possible to do this without making any unnecessary repetitions? Now, you do have to walk on some of these roads twice, but that doesn't count as a unnecessary repetition. So really I'm asking, can we visit all the dots without, can I just say it this way, without extra walking, right? We will have to walk down some of the streets twice, but not all of them. And I would like to do this without any unnecessary repetitions. Okay, so this one is made a little bit difficult just because I didn't actually draw you a graph. It's your job to look at this scenario and turn this into a graph. And I would suggest the graph involves, just like up here, the graph involves the streets, which I didn't really draw the streets. I really just drew the buildings. The streets go in between the buildings. So maybe I would start off by saying, okay, the graph truly is more like this. Although that last, it's mostly just like that, right? I mean, you could continue here, but you don't have to walk down here, so I'm not even gonna think about that, right?
Oh wait, you need to do one more in the middle to get the two.
Oh yes, thank you. Yeah, I also got to go like this. Thank you for paying attention more closely than I. All right. So this is basically where the streets are that we have to walk. Now, some of those streets we want to walk twice on. Like we're going to have to walk twice on some of them, but not all of them. And the way that I'm going to indicate that is these sort of red edges that I drew. The ones that I want to walk twice, I'll just draw two edges because my circle will have to cover this edge once and then again. So that would be like here. This one here, actually, I'm gonna put as if there were two edges there, because that street I have to go there and back to get both sides. All right, and then hopefully I will find them all. I also need two edges on this one because I have guys on both sides here. Also this one here and this one here, and I think maybe that's it. The other edges there you only want to walk on once. All right. So in this problem, I would say the trick is to read the original picture and sort of distill the graph that you want out of the original picture. It wasn't given to you explicitly. Anyway, the graph I want to consider here, I'm just going to redraw it, is I have these guys like this, and then an edge, an edge, an edge, two edges here, two edges here, two here, two here. All right, that's really the graph that I want to be thinking about here. And then it is on this graph. Sorry, this is a little sloppily drawn. I hope you don't mind. I'm going to try and draw it nicer. It is on this graph that I want to think about questions like what are the degrees of everything and so on. So what's the degree of this guy here? That would be 2. 2 edges touching this vertex. All right, let's just go through them. The next one over to the right, this is a 5 because I have 1, 2, 3, 4, 5, right? 5 edges around this one. Similarly, here's another 5. So that's a 5, that's a 5, that's a 2, a 3 up top. Up here is a 3, down here is a 4. All right, so this is the graph. I think now you can answer the question. Can we visit all the dots without extra walking? The answer is, show me the thumbs. It is no. I see some strong thumbs in the downwards position. Yes. You cannot do that because I have more than 2 odds, right? I will say there are many odds. So we require, I'll just say we will need to repeat some of these edges. All right, some of these edges are already kind of representing repetitions of individual roads. So that means we are actually going to have to walk down extra stretches of the road where we've already delivered all of the parcels. All right, we will need to repeat some edges. Again, you could ask a question like, well, what if I add an extra street? Then could I make it? I could say rather than, adding an extra street in a city block is not really possible. But I could say, if I repeated this edge right here, then I could do Euler path on the rest of them. All right, so that's something we could talk about. All right, any thoughts about that one? Excellent. That was mostly a review from the stuff we did last time and, some more examples. What I would like to talk about for the bulk of today is actually the next thing that you'll see on the checklist, which is called minimum duplication circuits or paths. Circuits or minimum duplication paths. Minimum duplication circuits and minimum duplication paths. We have already seen that very often when I ask you, like, can I do this without repeating the edges? The answer is often no. Like, actually, if you just draw a big graph at random, almost always the answer will be no, just because some of the degrees will be odd. So minimum duplication circuit, the idea behind this is when, let's just talk about circuits for now. When an Euler circuit doesn't exist, that means that if you want to do a circuit, you must repeat some of the edges, right? When an Euler circuit doesn't exist, that means some edges must be repeated, right? Because that's what Euler circuit means. An Euler circuit is one which does not repeat any edges. If I say that's impossible, it means you're going to have to repeat some of the edges if you want to cover all the edges. So when an Euler circuit doesn't exist, some edges must be repeated. And the natural thing, if you care about doing this in the real world, is you would like to repeat as few edges as possible, which you may not be able to get away with repeating no edges, but it still would be useful to repeat as few as possible. So when an Euler circuit doesn't exist, some edges must be repeated, and a minimum duplication circuit, is one which uses all edges, repeating as few as possible. All right, that's why it's called minimum duplication, because you are going to have some repeats in there, but it's the least number that you can possibly do. All right. So, for example, I'm talking about, and this is a new thing that we're going to have to learn how to think properly about, but the scenario is something like this. Let's say you're like Mr. Plow on this case, on this little grid here. Can we cover all edges with no repeats? Well, to answer that, you look at the degrees. They are all 2s and 3s here, except with a 4 in the middle. And there are, as usual, I am really sort of fixated on the odds because those are the ones which are obstacles. Can we cover all the edges with no repeats? The answer is no, because there are odds here, all right? So the answer here is no. because there's there's 4 odds. All right, once you know how to do this is a very easy question to answer. No, you cannot, because there's 4 odds. The thing that I want to talk about now is, okay, if you can't do this with no repeats, could you do it with only 1 repeat? Would that be possible here? Or maybe you have to do 2 repeats in order to make this work out. So the question is, what's the smallest amount of repeats possible? Specifically, I'm talking about repeated edges. So what's the smallest amount of repeated edges which would make it possible? And this is a more difficult question to answer, which is why I want to talk about it. And it's also, of course, very useful in the real world. If there's any real world scenario where you want to do something like this, and there is no way to do it without any repetitions, the natural next thing you're going to try to do is, okay, then I'm going to try to do it repeating as few as possible. All right. What's the smallest amount? Can you do this using only 1 repetition? Actually, because I happen to know how to do this problem already, I'll tell you, actually, this example, you must repeat 4 edges. You can't do it using only 1 or 2 or 3 repetitions. So in this case, it's not really obvious by looking at it, but I will just tell you the answer. In this case, we require 4 edge duplications. So my goal for the rest of today is just sort of, how do you figure that out? And then we'll talk about some variations too. Now here I'm talking about circuits. It's different if you're talking about minimum duplication paths, but that's something else. We'll get to that eventually. All right. This is the idea though behind minimum duplication circuits. I hope everybody's clear on the concept. Let's just try to look at some. This example right here is a little complicated. I want to look at a simpler example. Let's try something like this. This is just a smaller graph. All right. This is a graph. I'll write down the degrees. They are 2 on the top and the bottom and 3 on the 2 sides. All right. So because I see some odds, there's 2 odds in fact, that means there is no Euler circuit because of the 2 odds, right? That means if you want to do a circuit, you're going to have to do some amount of duplications. So next I start thinking about, all right, what's the smallest amount of duplications that I can do here? Here's the idea behind how we're going to think about this. As you do your circuit, you're going to have to redo some of the edges. You're going to have to duplicate some of the edges. So the question in my first question would be, what's the, I will say, best edge to duplicate in this case? If I had to go across one of these edges twice instead of once, which one would be the best to do it on? And I think you can answer this according to the degrees. Think about what it would look like if I added another edge. Now, you can't just add an edge no matter where you want. Anywhere you want, it has to be a duplication of an existing edge. But for example, if I were to duplicate the edge from the top 2 to the 3 on the right, this actually is not the best edge to do, because if I decided to go across that one twice, this would basically change the degrees in the graph. This now is a 3, this is a 3, this is a 2, this is a 4 now, all right? The 2 up here used to be a 2, but I add another edge there, so now it's a 3. Over here used to be a 3, but I added an edge, so now it's a 4. All right. Now, is this one any better in terms of not repeating edges? No, it is not. This still has 2 odds, so I would say that was a bad choice that I decided to duplicate that one, but it actually still has 2 odds here, so that was not a good choice. What was a good choice? I think if I duplicate the one across the middle, then these 3's will each become 4's, and everything will be even. All right, so actually this one right here, I would say that guy here was a bad choice to duplicate. All right, because all it did was give me 2 3's somewhere else. Versus a good choice would be the one across the middle. I'll draw it again. A good choice would be to duplicate the guy across the middle. Now, this used to be a 3, but now it's a 4. This used to be a 3, but now it's a 4. And these are still 2's. All right? That was a good choice. Now there are no more odds. And so I can make an Euler circuit on this one. So here, now they're all, they're all even. All right. So the moral of the story is the best edge to duplicate, if possible, it's best to duplicate an edge connecting 2 odds. Right? I had 2 in the original picture. I had 2 3's. And when I add that edge there, they become 2 4's, which is great. They're not odd anymore. That's what's good about it. So it's best to duplicate an edge connecting 2 odds. If you just duplicate an edge connecting 1 odd to an even, then you don't really solve any problems. You should duplicate an edge connecting 2 odds. Now they're all even. So this one here, I can make an Euler circuit in there now. And what does it look like? This is my graph. Same graph as before, but I've sort of doubled up the edge in the middle. All right? What that means is I'm actually going to have to repeat the one in the middle, but that's the one that I'm going to repeat, and I'm not going to repeat any of the other ones. So here I could say start up top. And because they're all even now, this should work out just fine. Go across the middle again. All right, you'll see I reused the one in the middle, but that was my plan all along. I decided which one to duplicate, and I did. All right. So now this right here, what you see here, has a duplication in the middle, but that's it, just one duplication. So this is a min-dup circ, a minimum duplication circuit with one duplication. Using one duplicated edge. You can see the one in the middle I went across twice, but all the other ones I went across once. All right. This is the idea. Any thoughts about this? So there's sort of a can I just kind of summarize here? To find a minimum duplication circuit, you make all degrees even by doubling edges. And I will just say parenthetically, it's best to double an edge between 2 odds, because then it turns the 2 odds into evens. Best to double an edge between 2 odds. There are some examples where this is not possible, and we'll talk about those, but on an easier example, then you can always do it in this way. Make all the degrees even by doubling edges, and then on that new one with some doubled edges in it, draw an Euler circuit on the new graph. And then that Euler circuit on the new graph represents a circuit with some duplications on the original graph. So draw an Euler circuit on the new graph. This represents a minimum duplication circuit on the original graph, the OG. G stands for graph. All right, a question? Yeah.
For example, if there wouldn't be there would be like numbers where not just two are odd, like it wouldn't be
Mhm.
a path and circuit, could it be also an exercise that we have to find an Euler path, like not even circuit because that would be
Yes.
impossible?
Yeah. Yeah, so we're also going to talk, right here I'm talking about minimum duplication circuit. There's also something called minimum duplication path,
Oh,
which
okay.
which is more or less the same, but let's just do, I wanted to do a few examples with the circuits first, and then we'll talk about paths in a moment. So let's try, I got a couple here to try. How about this guy? That's a nice looking sort of grid of roads. Let's find a minimum duplication circuit here. All right. So all the crossings are vertices, right? You should begin by looking at all the degrees everywhere, because that's the most basic thing that you need to focus on. So I hope that you are an expert of counting up the degrees. As I go across the top, it's 2, and then 2 3s, and then a 2. Remember, this is just the number of edges that are touching each vertex. Across the next row would be a 3, a 4, a 4, a 3. And then same again for the next row. And on the bottom, it's 2, 3, 3, 2. All right? And you should be focusing on the odd ones. So I don't really care about the evens, because I think of the evens as being like good and the odds are like bad. I want to get rid of the odds as much as possible. All right? Now, there are many odds, so I can say immediately, you can't do this just by duplicating one edge, because there's no way to turn all of these odds even by just adding a single edge in there, right? I would like, if at all possible, to pair up the odds and try to duplicate an edge connecting each of the odds in pairs. So let's try to, try to dupe edges connecting the odds in pairs. All right, anybody see a strategy to do that? I think this is not so difficult. I see someone making some hand motions. Remember, you have to duplicate existing edges. So I hope that you are not suggesting, let's just put an edge right there. That doesn't count as a duplication, all right? Ms. Road can do that, but that's because she is a trained professional road builder. We are talking about duplicating existing edges. So don't do that. You want to duplicate edges. I said try to duplicate edges connecting the odds in pairs. I think we can just do these two guys together, right? These two guys and these two guys. That would be 4 duplications. And that's the best way that this is going to work. So I duplicate here, 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 and here, right? Those are my 4 edges, which I'm going to have to duplicate. Once you duplicate those 4 edges, though, then it should be possible to draw in a circuit which covers all the edges and has 4 duplications. So this will require, in this example, this requires 4 dupes, right? And it is the ones in the middle, on the top and on the bottom and on the 2 sides. All right? Can we actually draw it? This one is maybe a bit of a pain to draw, but I'm going to try. I'm going to draw an Euler circuit, so let's just start up here. And keep in mind, I am going to duplicate this edge. Maybe I'll just like put a little neighbor next to it, a little neighborino. I am going to duplicate those 4 edges. Everything else I'm going over only once. Those 4 I'm going to go over twice. And as usual, you can more or less just try and draw this in, making it up as you go along, and it should work out unless you get very unlucky. So I'm going across there once. Maybe I'll just immediately go back across the same one. And I'm going to try to cover every little bit here as I go. How about I go up here, around there, maybe across and back. So there's my second duplication. You have to just keep in mind, remember which ones you're going to duplicate. I think I'm doing all right so far. You know, I covered this half. Now I got to go back, and I'll try and fill in all of those guys as I go back to the beginning point. I think it'll work out just fine. I'll go down here, back up here, up there, up there, up there. Maybe down this one, over here. I'm feeling good about this. There you go. So there's my minimum duplication circuit using 4 edge duplications. And it is not possible to do this with less than 4. Because you can tell it's not possible to pair these guys up using, say, only 3 edges. Because there's 8 odd numbers there. You can't get to all of them using only 3 edges. All right? This is how we do it. I got one more. How about you guys want to try this one? I will give you a moment. Maybe I'll walk around and see how you're doing. Let's say there's a vertex in the middle there. All right. See if you can find a minimum duplication circuit. Your first order of business should be to figure out the degrees and then decide for yourself which of the edges you're going to duplicate. Walk around. Choices. Decide which ones you want to duplicate first. Should. Yeah, which ones are you? Yeah, that'll do it. So you can either do this one, that one, or do that one, that one. Yeah. Yeah, either.
I wouldn't do it all.
That's right, yeah. In fact, this, like when you do this, it turns out to a 4. If you also did that, it would become a 5 for each rest. Good idea. Now see if we can, draw in the circle.
Oh, yeah.
Good? Yeah, good choice. So which ones did you do? Here.
Yeah.
Jesus Christ, it's like
Oh, so you want to use your two sides? Oh, okay.
Mm-hmm. Yep. How's it going? Alright, so it's duplicated at the bottom and top. Okay, so it looks like people are feeling good about this. So you start by looking at the degrees. You identify the odds in there. That's here, 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 and here, right? Now, I'm going to have to duplicate some edges to turn those odds into evens. And the strategy is either duplicate the top and the bottom edge, or you could duplicate the 2 side edges. Either one will lead to a correct answer, although your answers will look different. How about I am going to duplicate the 2 on the sides. So that makes this 3 into a 4, this 3 into a 4, and also those 2 3s into a 4. Make sure you don't like overdo it. If you also duplicate the top and the bottom, that screws it up, because then this 4, if I also put this in, then this 4 becomes a 5, and I don't want that. I want it to be a 4, not a 5. So don't do that. All right, this is what I want. I can tell at this point that it requires 2 duplications. 2 dupes. Right? As I'm doing it, it'll be the left side and the right side. Although some of you, as I was walking around, did it on the top and the bottom, and that's fine too. So to actually draw my answer then, all right, this is my graph, keeping in mind that I'm going to do each of the 2 sides twice. I'll start up here maybe, and then draw my lines the way I do. So there's one duplication on the side there, and then this side is also duplicated. There you go. That's my answer. Your path probably looks different from mine, but that's how I did it. Anybody got questions about that? Excellent. It's not so hard to do if you know what you're looking for, all right? Sometimes if I want to make it a little easier on you, I might just ask, how many duplications are necessary? Then you could say this and stop, leave it at that. You could just say 2 duplications. In that case, you wouldn't have to draw this part, which sometimes this can be the hardest part, just like in this example especially, that it could be a little tricky to figure out where the line has to go, all right? Okay, what about, there's one situation that could make this a little bit more difficult, and that would be if the odds do not naturally pair up. Like in this example, I had the odds, and I basically took the 3s 2 by 2. I took these 2 3s together and these 2 3s together. There are some cases where the odds do not nicely fall in pairs like that, and here is an example. It's not so hard. You just have to know how to handle a case like this. How about this? This is like a little sumo wrestler guy, what I imagine this looks like. All right. Again, I want to find a minimum duplication circuit. Find a min dup circ. All right. So we should begin, as always, by figuring out all the degrees. A corner like this is a 2, so I got 2s, 2, 2, 2, 2. These are all 2s also, right? And then three-way junction is a 3. I see that here is a 3, and also over here is a 3, the 2 sort of shoulders. And then the 4-way junctions are 4s. That's a 4, that's a 4, that's a 4, that's a 4. All right? Yes?
I think you could draw the between the 3 one, and then between the 4 another one. Because
Between the 3?
the 2 3s, you can like duplicate this line.
This line going all the way across?
Yeah. And then in between the 4 again, just the 4.
I would say, I think you have the right idea, although I would say there isn't really a line going all the way across here. When I drew it, I drew one line, but really this is 3 edges end to end, right? So you can't really think of the 3 as being, this 3 is not connected by an edge to this 3. And that's what makes this this one more difficult. So in this case, the odds are not connected by an edge. Right? In all the other examples we've seen so far, it was the case that each odd was just next to another odd with one edge, and you duplicate that edge. In this case, there's actually sort of 3 edges in between them rather than just one edge. The odds are not connected by an edge, so that's what makes this harder. How you get around that is the best strategy in this case. Can I just say, so we need more than one duplication, right? We need more than one dupe. The proper strategy to use in this case is you find a path connecting the threes. Find the shortest path connecting the odds up. Connecting the odds. All right. And then duplicate all edges along that path. All right. So what I mean by that is, look at this picture. I have those two threes which are kind of far apart. How far apart are they exactly? Well, I can get from this one to this one on 3 edges. Go 1, 2, 3. And I'm going to duplicate all of those edges. Let's see what happens. So in this case, it looks like this one, this one, this one. All right? A path from one 3 to the other. And you want to do this using as few edges as possible. Of course, you don't want to find like some giant path over here. You duplicate all of the edges along the path. What are the degrees now? How did we change the degrees? Every time you do one of these duplications, it increases the degree. So the 3 on the left used to be 3, is now 4, because I added an extra edge there. So this is now 4. How about the 4 over here? You may be worried because this is now a 5, right? Because I added a new edge there. Anybody not so worried? Yeah?
It is a 6 because both, so it's fine again?
Right. It's actually a 6 because I added 2 edges there. All right. It used to be even, but I've added 2 more, so now it's a 6. So everything's cool, right? This is no longer 4. This is now a 6. This 4 also not a 4 anymore. It's a 6, and this 3 is now a 4 because it's only one more edge right there. All right. This is how this works out. If you duplicate all the edges along a path, you're going to change the odds into evens, and all of the intermediate evens will stay even. They will get bigger, but only bigger by 2, which means they will still be evens. All right? So we find the shortest path connecting the odds and duplicate all edges along that path. So in this example, we require 3 duplications, right? And it's going to be those 3 edges across the top there. So here we use 3 duplications. And I'll try and draw my minimum duplication circuit here. So let's start over here. And reminding myself, these are the ones that I'm going to do twice. All right, let's see if I can do this. Like I said before, sometimes what I'm doing right now is the hardest part. It's not so bad if you have a little bit of practice. But I'll go there. This graph is kind of complicated. Hopefully I haven't screwed it up yet. Go around the top of the head, round across the middle, back. There you go. I think I did it. This is 3 duplicated edges. It's sort of these shoulders here and the whatever that is across the middle. All right. There were 3 duplications that time. All right, so the best case scenario is when you can just pair up the odds and connect them directly. But sometimes you're going to have to connect along paths rather than directly. All right. Can we just take one last look at the very first example I showed you, where I said this one actually requires 4 duplications, although it's not obvious why. So let's just look at that one again. That was this one. It was just this. So the odds here, I don't care about evens, but these were the odds. And the problem here is you cannot just like before, you can't directly connect up the odds in pairs because each of these odds, they are not next to each other. Like they don't have a single edge between them. So your best strategy will be to duplicate paths connecting these 2 odds. And there are a few different ways to do it, but I think a good way would be if I join these 2 guys together, not by drawing the diagonal, because that's not allowed, but I can duplicate here followed by here. All right, so I'm going to duplicate this guy and then that guy. That's 2 duplications. And then the other two can be handled by duplicating the other sort of corner pieces like that. All right? So this one requires 4 duplications. Yeah?
Could we also duplicate these two?
Yeah, you can also go across the middle. There's many ways to do this. You could go duplicate like this and this. That's still 4 duplications. Or you could even do, there are many options here. You could go like this and like this. That's some kind of mixture of those two.
Just like this?
I think that's that, right?
Oh, yeah. Sorry.
Yeah. Yes, any of these would work out, but in any case, these all require 4 duplications, all right? So if I asked you, if the question, say on the homework or something, was just how many duplications am I going to need, you could just go this far and say I need 4 duplications. If I asked you actually like show me the minimum duplication circuit, then you actually got to draw it in, you know, like I did on that thing. All right. Excellent. We got about 20 minutes left. I think that's more than enough time to discuss. Everything I've said so far has been about minimum duplication circuits. Can we just talk briefly about minimum duplication paths? That is almost the same thing, but you just have to know how to handle the difference. What about minimum duplication paths? Not circuit, all right? Minimum duplication path means it starts at one place and ends at a different place. It doesn't have to be a circuit anymore. But still, this minimum duplication thing, it means I want to start at one place, end at another place, while repeating as few edges as possible, all right? So we want to make a path with as few dupes as possible. A path, not a circuit. All right? Yeah.
Is it just doing the same thing but leaving 2 odd degrees?
That is exactly correct. If you want to make remember, if you want to make an Euler circuit, you can't have any odds. But if you want to make an Euler path, there can be 2 odds and the rest even. So the answer is we do all the same stuff, only you can leave 2 odds. You don't have to make everything even. So make a path with as few duplications as possible. I will say this is just like a minimum duplication circuit, but we can leave 2 odds and make the rest even. That's the only difference. All right? So for example, like that one that I just talked about, how about this thing? Where the odds are here, 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 and here. Let's make a minimum duplication path. All right? Again, we have to duplicate edges to turn the odds into evens, but we don't have to turn them all into evens. We can leave 2 odds. So to make a minimum duplication path, I need to make all but 2 odds, right? And I can just decide, you know, unless I tell you, you can just sort of decide for yourself which ones you're going to leave as odd and which ones you're going to duplicate to make them even. So maybe I'll leave the upper right ones odd, and I'm going to duplicate edges to make these 2 even. And in order to do that, I'll go around the bottom left corner. So I will duplicate here and here, which makes that into a 4, and that into a 4, and this into a 4. All right? But I leave the other 2 as odd, because that's fine when I want to make a path rather than a circuit. All right? So those are my duplications, and then my minimum duplication path. I'll draw it this time. Looks like, so here's my graph. where I'm going to do that one twice and that one twice. Where should I start? When you're doing a path, it does matter where you start.
On one of the not even ones.
Yeah, one of the odd ones. So you either got to start here and end here, or you start here and end here. This is how you it always works out on a path. So I'll start off at the top one, the one in the top in the middle. And if I do it correctly, I will magically end up at the middle on the right. So let's try and do it. And I am going to duplicate those two. Like I said, I'll just do it right here. Go right back across. And as usual, if you're doing this also, you will probably get a different path, but I hope you can make yours work out just like I did. All right. That's how we do it. This is a minimum duplication path. All right. I got one last really big one. We have 15 minutes, but I don't think we need that much time. Let's try a really big one, and that'll do it for today, of a minimum duplication path. After this, I want to talk about something completely different, so this is a decent stopping point. Here's a big one. This I'm thinking of as a big city block, maybe, with some diagonals. It has, let's say, a diagonal here, a diagonal here, and a diagonal here. All right. Let's find a minimum duplication path here. Or let's actually, just to make it easier, let's just answer how many dupes are necessary. How many dupes are needed and where to get a minimum duplication path? Sometimes when people talk about these, they are referred to as optimal parade routes. That would be thinking of this as like a city block and you want to have a parade, like the 4th of July parade or something. And the best possible parade route would be if the parade actually walked down every street once, right? Wouldn't that be awesome? Then all the little children could see the parade go by from their own house. Of course, if you want to do that, you're probably going to have to walk back the same street twice, which is not really good for a parade to do. So this minimum duplication path is sometimes called an optimal parade route. Anyway, let's see if we can answer this. So I just asked how many duplications are needed and where would they be. This one would be a pain to actually draw in the red line, but we can still talk about how many dupes do you need. So anyway, we look at where are the odds. That's what matters here. I see an odd vertex here. That's a three-way, right? Any three-way intersection is an odd. So that's an odd, 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 an odd, an odd. All right. This in the corner down here is a three-way also, so that's an odd. Any four-way intersection is 4, so that's an even. Any more odds in here? Yeah?
There's 2 5s.
Yeah, there's some 5s. So here is like a 4-way, but with an extra. So this is an odd. That's a 5 right there. I see another 5 here. Actually, I see one more 5. Also here, right? That's a 4-way intersection, but with an extra leg. I think that's it. I think these are all the odds, okay? So at a glance, I can tell you this is probably going to require many duplications, right? Not just like 1 or 2, because there's way too many odds here. You have to make duplications to sort of repair all of the odds. But not all the odds, because I'm talking about path, remember? We're going to leave 2 odd and try to connect up the rest. Come on now, the rest, right? So there are many ways that you can do this in this example. You could try to think of for yourself, first of all, which 2 am I going to leave odd? I would like to leave them odd, the ones which are the least convenient to connect up with the rest of them. Now, I actually don't see 2 natural candidates, but I do see one that I definitely think would be inconvenient to handle. Anybody agree? I see one odd that's kind of a pain to connect up to the rest of the odds. Yeah?
Is it the one at the top?
Yeah, the one on the top. Yeah, this one is not naturally right next to another odd, whereas all the other ones are. So I'm going to leave this one as an odd. I guess I'll have a leftover odd down here somewhere, but whatever. We'll see about that. So I'm going to keep the one up top odd. Maybe I'm a little bit worried about this guy, right? This guy can only connect directly to that one. So maybe I will make sure that's going to be one of my duplications. That handles those two. And then you just have to try to pair them up in some natural way. And I think it's not so hard. There's many ways to do this. How about I take this diagonal here, maybe these two guys at the bottom, maybe this diagonal here, and these two guys over here. All right? I think I have now paired them all up except for two of them. Okay? So these blue ones in here that I drew, that's where the parade is going to have to walk that street twice. So, you know, get all your little friends and line up on those streets because you're going to see the parade twice if you go there. All right? Connect up the rest. Anyway, can we actually answer the question here? How many duplications are needed? What do you say?
It's 5.
5. Yeah. Will you give me the fingers? Or was that yes, 5. I had to duplicate 5. I left 2 like that. So we need 5 duplications. All right. And where would they be? I mean, I drew where they would be. Of course, there are many other strategies you could have used to place them elsewhere that would still be correct. All right. And I think this is all we need to say for today about duplications. All right.
This out would be a nightmare.
Yeah, it would be a pain to draw the line in. So that's why I didn't ask you to. All right. Have a great weekend. We will have homework due as usual next week. So check it out.